fact that I don't know how to, what explicitly can I relate to the vertex algebras which I use in my talk. Okay, I start from the classical, well, at least a well-known object, W algebras introduced by Fateev and Lukyanov. I wrote here W of GLN hat. I use a little bit non-standard notations. Usually Wn is related to SLN hat, and therefore W2 is just Virasoro without additional Heisenberg, but it's not very important, and such notation will be more convenient for me. I here wrote relations for Heisenberg and Virasoro algebra, which of course standard. There are different ways to define for this algebra. I mean that for n greater than 2, it is more or less impossible to write this algebra in terms of generators and relations. So we need to have another way to think about this algebra. And there are different approaches. One of them was more or less initial approach by Fateev and Lukyanov. This algebra is defined as a subalgebra of the n-dimensional Heisenberg algebra, which commutes with certain operators which are called screening operators. They are given by integral of a certain exponent. Another approach is a so-called Drinfeld-Sokolov or quantum Hamiltonian reduction of GLN hat for certain important element. And one more approach is a cassette construction of this algebra. First and second approach are really close. It is, in many cases, it is possible to see that this Sokolov reduction is more or less the same as the screening construction. But this approach is, in my understanding, a little bit different. In my talk, I will use the screening operator approach when I talk about W algebras. And one more known fact that this algebra has representations, for example, Fermat modulus, and these modulus are essentially Fock modulus of the Heisenberg algebra. And its character is the character from n of the Fock modulus of the n-component bosonic field, if you want. Or in a more combinatorial language, it has a basis labeled by n-tuple of partitions. Delta is a conformal dimension, which are given in terms of parameters, but this formula is not essential here. Okay. Next, due to a GT relation, or I write mathematical term, geometric representation theory, we know that such double algebra has geometric interpretation as an algebra which acts on the direct sum of equivalent cohomology of the modular space of instantons. These parameters A are parameters of the framing of the instantons, and epsilon 1 and epsilon 2 are equivalent parameters on C2, or omega deformation parameters in more physical terms. For such equivalent cohomology space, we have a distinguished basis labeled by points fixed under the action of the torus, with respect to which we take equivalent cohomology. And what GT conjecture, GT statement in particular means that W conformal blocks are equivalent to the certain sum of these special points, and these special points correspond to special bases in this Fermat model. Some of the certain explicit terms. Okay. They're given by explicit combinatorial formula, Nekrasov formula. And if the previous part was for generic parameters, A1, so AN, and also generic epsilon, epsilon 2. If parameters become special, we have certain resonances, and in the next slide I'll give you an example of such resonance. Then this function becomes ill-defined. it have zeros and in numerator and in denominator. And we need, and from the point of view of representation theory, it means that the representation becomes reducible. So if we take the quotient, then only part of the combinatorial of the n tuples of partitions remains. So we will have a basis which will be labeled by partition with additional condition. I maybe want to note that this geometric basis is very suitable to such quotients. It is a good property, I mean, for this basis. Okay, now I give an example of such resonance. It's if difference between two A's is a linear combination of epsilon 1 and epsilon 2, and these numbers RL and SL are assumed to be non-negative integer, then restriction of the n-tuple of partition looks like this. In terms of conformal theory, I'm speaking about generic. I'm not impose any resonance on epsilon 1, epsilon 2, so I'm speaking about generic central charge, but for the degenerate representation, about degenerate representations. Okay, and this combinatorial condition can be rewritten in terms of more geometrically as a condition that we can write a plane partition. So here on the first row, I draw first partition alpha 1 first, alpha 1, 2, and so on, shifted by certain number nu 1. On the second row, I draw the second partition alpha 2, alpha 3, and so alpha n. Now, these shifts, nu 1, nu 2, and so on, are given in terms of these numbers r. I go to they equal to the sum, so such that the difference between nu 1 and nu 2 is just r1, and so on. And these shifts are given in terms of these numbers s. So it is easy to see that the standard plane condition for plane partitions, that each number is greater to this to two neighbors, is equivalent to the condition that alpha 1 and so alpha n are partitions, and this additional condition. So we have plane partition with a base with this infinite rectangle of this size n minus a certain diagram lambda. Or you can think another way, that this lambda is filled by infinity. So we have plane partition with two asymptotics, one in the right direction and another is this direction, and with the condition that this plane partition has only n rows. This okay, and now I go to the main combinatorial object of my talk. I will discuss plane partition with a condition which we call PEAT. It is a plane partition which has asymptotics along all three coordinate axes, and additional conditions that certain box is forbidden. Now I discuss the case where this box lies on the first on the x or y plane. Here is an example. So this is a forbidden box. This box has coordinates m, m plus 1, n plus 1, 1. So in terms of plane partition, this condition is written here. Okay, here is an example, and I specify, in this example I specify lambda, nu, and mu. As usual, three-dimensional diagram is related to plane partition. In each box I wrote the height of the corresponding column. A previous example, which corresponds to standard W algebra, is a case where one of these numbers, say n, equal to 0, or maybe say m equal to 0. So we have this pit is near the wall. And now the pit lies inside our plane. And maybe I decide to state in Z1 that correspondingly algebra will be denoted by Wn m, and they are somehow related to superalgebras, and this is the subject of my talk. Okay, this is a definition of the object. Okay, so first, if I look to this in a combinatorial manner, then the first question is to calculate generating function. Just count the number of such plane partition with a q in power number of boxes. Of course, since we have asymptotics, the number of boxes is infinite. We should substitute this infinity. It is not easy to define this number of boxes, and I will skip this. And I will use notations. Hi, lambda, mu, nu, m, m is a generating function of plane partition which satisfies conditions given on the previous slide. So this lambda, nu, mu are asymptotic conditions, and n, m is the position of the pit. Okay, so first, what is known? First known result is not about pit condition, just about the plane partition with 3 asymptotic conditions. This is a formula due to Konьков-Waffer решетихин. So theoretically speaking, what we calculate is some sort of finitization of this formula, and then in principle, if n and m goes to infinity, our formulas will reproduce this formula. Second result is also very known. That if we put pit near the wall, so just consider plane partitions with n rows and without asymptotic conditions, with empty asymptotic conditions, then the generating function has a nice formula as a product. It's McMahon formula. If this plane partition, if this pit is located near the wall, there is a, I think also well known, but I don't know what is the best reference, formula, which is generalization of this formula. It is no more product formula, but here we have certain power of q, which is just the subject of the definition of the grading. We have the product, and we have numerator of the Schur polynomial. We have alternant here. We have determinant here. If one of the partitions, nu and lambda, become empty, then the determinant is a Vandermonde determinant and can be calculated, and we'll have product formula. If not, this is just the determinant of the size n times n. And probably I should say here that I said it before, but implicitly, now I would like to say it explicitly, that these functions are characters of the Wn algebras, characters of the reducible representation, but for generic central charge. Okay. Now I would like to give an answer. I put here one because I have 2 slides for answer. First in the partial case, special case, and then I'll show something about generic answer. But before, I would like to say what can we say about these partitions, nu, mu, and lambda. So due to pit condition, nu has no more than n elements. So it corresponds, from the representation theoretic point of view, it corresponds to fine dimensional representation of GLN. And the same for mu. And lambda has a condition that it is located in the hook. So representation theoretic meaning of this condition that it corresponds to a fine dimensional representation of the superalgebra, GLN-M. And I put word tensor, which means that there's a special class of representation which appears in the tensor product of the standard Cn plus m. The representation theory of the superalgebra is more difficult than for standard algebras, but there is a certain class of representations which is very similar to standard finite dimensional representations, and this is a class of tensor representations. Okay, now at first I'll give a formula for empty lambda without asymptotic conditions in this direction, and even for n equal m, just for simplicity. Actually, we have two formulas. Here I introduce some notations, so n is new parts of nu plus rho, the same for m. And we have, on the second formula, we have summation over additional partition alpha. So we actually have, we have two formulas. One of them is a determinant, and another can be viewed as a calculation of the such determinant, or it can be viewed as a so-called bosonic formulas. In the second formula, we have a summation over alpha, and here's the product of something like Schur polynomials for partition alpha plus rho and partition minus alpha minus rho. Or, if you want, mu plus rho and mu plus rho. Here is a duality. As usual, if I state that this is a character of certain algebras, then I want to have a representation theoretic interpretation of such formulas. And both formulas admit such, at least conjectural, representation as a other characteristic of the certain resolution, like BGG resolution. Okay. But now I want to stress the similarity between these formulas and formulas for characters of this superalgebra, GLNM. Since lambda is responsible for character of GLNM, and here lambda is empty, so I'm talking about trivial representation. But trivial, it's not a problem. There are formulas for such representation. And next slide, I have in the next slide, I write formulas for generic lambda, and they are found by Mons van der Jocht, based essentially on the Katsura-Kimoto formula. And another second formula follows from the result of this paper, and they are similar. Here we also have a product of Schur functions in alpha and minus alpha, some standard factor, which can be, like here, we have product. Parameters nu and mu, of course, do not appear here, but instead of them, we have here x and y. Exact x and y coordinates on the Cartan subalgebra of GLNM. We have n parameters x and m parameters y. Okay. Now, this is a general answer. How can I comment it? Okay, I comment a few details. So first of all, here I introduced one notation r. R is an integer which labels the representation theory. Name of this number is the degree of atypicality of the representation corresponding to lambda. This integer measures difficulty of the corresponding representation. This integer goes to 0 to minimum of m and n. If r is 0, then the corresponding representation is called typical, and all story is very simple about this representation. For example, here we have summation over alpha, and alpha is now a partition of r parts. If r is 0, we have no summation, and the character is just a product of the two characters, character of a GLN and character of a GLM. Previous case where lambda is empty was correspond to maximum value of alpha. So from the point of view of representation theory, it is the most difficult case. Again, we have two formulas. One of them is determinant. Now this corresponding matrix is rectangle. Has a block form. It consists of 4 blocks, but one of them is 0. And here's just a certain degree of Q. And here we have some. I don't know how to call this function. There is notion of half set of. If we have here we have summation over all integer over non-negative integer. If we have summation over all integer, I will call it theta function. But this is something like half theta function. Here I wrote the formula just to look similar, but this is just the rational function 1 over x plus y. combinatorially, okay, so now I'm talking about the combinatorial result. It can be proven just using combinatorial methods, and the corresponding method here is a non-intersecting path, Lindström-Gesell-Viennot formula. And for this formula, we use so-called Brion's theorem, which calculate integer points, generating function of integer points in the polytope. Of course, it is easy to see algebraically that these two formulas are equivalent as well as here. And okay, conjecture that this equivalence of the Dinfeld-Conock or Jean-Luc type between representation of such W algebra and product of three quantum groups. One of them is responsible for lambda, another for nu, and third for mu. And these parameters, of course, should be related. They are given in terms of epsilon 1 to epsilon 2. So essentially, we have one parameter. This is analog of the known fact that the representation theory of W algebra Foteyev-Lukyanov is related to the representation theory of two quantum groups, GLN, or if you want, modular double of GLN. This is some sort of modular double, but you see here we have not double but triple, and of different algebras. This is what I wanted to say about combinatorics, and now I come to the W algebras, and I would like to say a few words. How can we see these quantum groups, especially the super algebras in more algebraic language, and we can see that, but after Q deformation. And this Q deformation also provides some explanation why such representations are interesting. Maybe provides. I'll start from the quantum toroidal algebra GL1. I didn't write it. Of course, if I omit the generators and relations of this algebra, as an idea, okay, probably many people in the audience know what is it. This is something like a quantum toroidal SL2, but for another function. In quantum toroidal SL2, we have just one factor in numerator and one factor in denominator. And here we have product of three factor here and three factor here, and where Q1 and Q2, Q3 are parameters by this relation. This idea that this is something like SL2 can be rephrased as this is given by Dinger-Haar construction. This algebra is given by Dinger-Haar construction. This algebra acts on the K-theory of instanton moduli spaces. I will not use it. I will not use it, but use it. I mean, this algebra has Fock representations, and this is K-theory of Hilbert's-Heim. What is important for me is that this, for such Fock representations depend on the one continuous parameter, spectral parameter. And also it has certain central charge equal to Qi in power 1 over square root of Qi. And this algebra is symmetric under the permutation of Q1, Q2, Q3. So we have three types of Fock representations. This simplest representations, if you want to have more difficult representation, one can take tensor products. For example, first take tensor products of the representation of the one type. Geometrically, this corresponds to K-theory of U1 instantons on C2. And the image of this algebra in this representation of the endomorphism of such model is the Q-deformed Wn algebra. This was proven by 6 years ago. And what was the idea of the proof? Idea was based on the fact that the image of this algebra is the tensor product of two models commutes with two screening operators. I don't know, S plus and S minus. And this S plus of Z, this screen current, is a certain exponent here in terms of Heisenberg algebras acting here. If we have tensor product of n factors, then for each 2 consecutive factors, we have a corresponding pair of screening operators, s plus minus, s plus and s minus, and by this I plus 1, I denote the position of these 2 factors. And due to the construction of the coproduct, the image of this algebra should commute with with all these 2 n minus 2 screenings. It is convenient to decompose them into 2 parts, and screenings from different parts at least formally commute with each other, and screenings of 1 part generate, okay, to be honest, something like an important subalgebra of the quantum group, quantum GLN. And screening of the second part generate an important algebra for another quantum GLN with the parameters q and q prime related somehow. So what I have said, that so it is not difficult to see that the image commutes with such screenings, and this is enough to say that the image is Q-deformed WN algebra. And due to definition of Feigen and Frenkel. And one more sentence that these 2 systems of screening tells us about this GLN symmetry. Now we consider product of models of 2 types. If we can take the product of one model first type and another model second type, then there is only one screening which commutes with the image. It is a fermionic screening. And using this screening, we can in this case we can write all screenings which we have and decompose them to 3 commuting families. And this screening corresponds to GLN, this GLM, and this is correspond to superalgebra, this additional fermionic screening. Okay. You can ask about next question. Okay, here I used models of the 2 type. Here I can use models of the 3 types. Tensor product of n models of first type, m models of the second types, and k models of the third type. Again, so in terms of the plane partitions, this will correspond to the forbidden box and the with coordinates n plus 1, m plus 1, k plus 1. And using screening description, we can argue that the corresponding quantum groups are all 3 will be super groups with these parameters. If I take limit q goes to 1, this Q-deformed double algebra goes to standard double algebras, and essentially all of them are quotient of the certain W infinity algebra. This is somehow limit of the fact that all these representations arises from the one quantum toroidal algebras. And this classification result, there is no other quotient of such algebra which can be defined by the screening construction. Okay, I think I more or less should stop. This is the last slide about further questions. I put here 2 questions. One question is that how to find another algebraic construction of this algebra, which I mentioned in the beginning, quantum driven physical reduction or concept construction. I mean, different construction can help us to see different properties of the representation. And the second question is what is the relation to the instantons in supersymmetric H series? And I put here one remark that our Pitt condition means that we study monomial ideals which contain certain monomial. So it looks like we study ideals on the surface given by this equation that this is equal to 0, some singular equation. But this is a remark and I don't know what to do with it. Anyway, this.
Questions? Maybe remarks? Well, I have a remark. So The answer to your last question, of course, the supercast Moody algebras like GLN/M can be realized as acting on de-facto operators on in the theories on folded spacetimes, where you have two surfaces intersecting transversely inside a three-dimensional space along a curve. And so you can have a rank n theory on one component and rank n theory on another component, and then there is a defect which leaves it in this intersection, and there is a GLN/M algebra living there. And so it seems that you're realizing this using three-dimensional partitions. Okay, if there are no more questions, let's thank Misha again. We're off for the break.